Okay, so welcome to my talk. The title is a sublinear time framework for geometric optimization with outliers in high dimensions. So in this paper, we focus on enclosing problems, which is a fundamental topic in computational geometry. We consider the simple example first. Minima enclosing ball. Basically, you are given a set of points in the Euclidean space, and you want to find a ball to cover all the given points. And we want to minimize the radius. So basically, the smaller the radius, the better the solution. And here also several other examples for enclosing problems, like k-center clustering. Basically, we want to find k-balls to cover the given set of points, and we minimize the maxima radius. And the second example is minima flight fitting. Basically, we want to find the low-dimensional flight to fit the given set of points. So here we want to minimize the maxima orthogonal distance from the given input to the central flight. So you can view this problem as a generalization of minima enclosing ball. For minima enclosing ball, the ball center actually is a zero-dimensional flight. But here we generalize it to a low-dimensional flight. And the third example is one-class SVM. It's a maximization problem. Basically, we want to find a half space to enclose the given set of points and maximize the orthogonal distance from the origin to the boundary of the half space. Basically, the boundary is a hyperplane in the space. But in reality, we often need to consider outliers. Like for many real-world data sets, they often contain outliers. Even one single outlier could significantly change your result. And also in some scenario, like for SVM, we want to train a model for classification, but some attacker may want to change your decision boundary, right? So he may inject some special point to your training data to change your decision boundary, so that when you do testing, you may get some misclassification. So that's why we consider outliers for the minima enclosing problem in this paper. First, we consider the simple example, minima enclosing ball with outlier. Here's the formal definition. So suppose we are given a set of n points in d-dimensional space. The dimensionality d could be very high, and also a parameter gamma between 0 and 1. We want to find the smallest ball to cover 1 minus gamma times n points. So that means we allow gamma n outliers. For example, if gamma is equal to 10%, that means we allow 10% outliers, and we want to cover at least 90% of the input. And also in this paper, we consider the general problem, which is called minima enclosing X with outliers. So here, the ball is replaced by X, which stands for a specified kind of shape we will discuss later. So we focus on minima enclosing ball with outliers first. We consider developing sublinear time algorithms for this problem because when we handle big data, sometimes we may be unable to read the whole data set by one pass. So we need to develop some sampling algorithm to have the complexity sublinear in the input size. And actually, for the case without outliers, like the ordinary k-center clustering or the ordinary SVM, there are some existing algorithms having the time complexity sublinear in the input size. So here I list several references here. But how about the case with outliers? But actually it's easy to obtain a sampling algorithm based on the theory of VC dimension. But if we use this approach, the sample size will depend on the dimensionality. Because we consider the high dimensional case, the dimensionality d could be very high. So in this paper, we also design the sampling algorithms for solving those problems. But our sample size is independent of the dimensionality. So this is a key difference. Okay, Um, First, we know that it's easy to achieve a true approximation for MEB with outliers, right? Because suppose you just randomly pick one point from the input, and we know that um, with certain probability, the selected point belongs to the side of optima in layers. So if we use the triangle inequality, we know this point will result in a true approximation. So it's a very easy idea. But in our paper, we built an example to show that it's impossible to achieve an approximation ratio less than 2 if we require the sample size to be independent of n. So in this paper, we tend to focus on the back criteria approximation. So here we have two parameters to define the back criteria approximation. First, we require the radius to be less than 1 times 1 plus epsilon times ROPT. So here ROPT means the optimal radius. And also we require the ball to cover at least 1 minus 1 plus delta times gamma n points. So that means we allow a slightly larger number of outliers. You know, in the definition, we allow gamma n outliers, but now we allow a slightly larger 1 plus delta times gamma n outliers. Okay, so this is an outline for your for my remaining part. First, I will introduce the cosine construction algorithm for MEB from Badu and Clarkson, and then we will introduce the linear time algorithm based on the cosine construction idea. And then I will show you 2K lemmas proposed in our paper for improving the running time from linear to be sublinear. And finally, I will show you some extensions for the general MEX with outliers. Okay, so this is a brief introduction for their cosine construction idea. In the algorithm, actually it's a very standard greedy algorithm. In the algorithm, we always maintain a cosine ice, and which is empty at the beginning. And in each step, we compute the approximate center OI of the cosine ice, and then we select the furthest point, say P, to the center OI, and we add it to the cosine. So eventually, after running this idea 2 over epsilon steps, we can build the cosine, and also we can obtain the 1 plus epsilon approximate center for the whole input. Okay, so how to apply this cosine construction idea to MEB with outliers? You know, the challenge is that the inlayers and outliers are mixed. So we don't know who are inlayers, who are outliers. So it's a highly combinatorial optimization problem. But here we have a simple observation on their cosine construction procedure. We found that it's not necessary to always add the furthest point to the cosine. You know, in their cosine construction, we always select the point who is the furthest to the current center OI, and we add this point to the cosine. But actually, this is not necessary. We just need to find a point who has a distance larger than this threshold, 1 plus epsilon times ROPT. That should be enough. That should be sufficient to guarantee the convergence speed. Otherwise, if no such point exists, that means a 1 plus epsilon approximation is already obtained. Okay, so based on this simple observation, we can introduce our linear time for MEB with outliers. Suppose POPT is the side of optima in layers. But we should emphasize we don't know who are the optima in layers. But we just use this symbol to denote such a site. And so in each step for updating the cosine in their construction, we let Q, big Q, be the side of 1 plus delta times gamma n furthest points to OI. And then we just randomly pick one point from big Q, say it's a small q, and then we add it to the cosine ice. So first, it's very easy to know the small q belongs to the set of optimal inlayers with a probability at least delta over 1 plus delta, because there are so many points, 1 plus delta times gamma n points in big Q, but there are only gamma n outliers. So that's why this probability is at least a delta over 1 plus delta. And then we consider two cases based on the simple observation I just mentioned. If this distance between Q and OI is larger than this threshold, then the BCS construction still works. So that means we can just safely add this point to the call site, and the convergence speed are still guaranteed. And for the other case, if the distance is less than 1 plus epsilon times ROBT, that means a back criteria approximation is already obtained. But for this approach, we need to pay attention to the success probability, because the whole algorithm is based on random sampling. So for each step, the success probability is delta over 1 plus delta. And we run the construction 2 over epsilon steps. So the overall success probability is delta over 1 plus delta to the power of 2 over epsilon. So that means if we want to keep the success probability to be a constant value, we need to repeat the algorithm so many times. Basically, each time we get a candidate solution, and we need to select the best candidate solution as our final result. Okay. So now we consider how to improve this linear approach to sublinear. Basically, we have two key issues. First, we need to, in each step, we need to select the site big Q. Obviously, this step takes linear time, right? Because we need to read the whole data set by one pass. So it obviously needs a linear time. And second, because we need to repeat the algorithm multiple times to guarantee a constant success probability, so we get multiple candidate solutions. So for each solution, we need to compute its objective value. So that means it takes a linear time. So for this part, we also need to run the whole approach in linear time. So how to resolve these two key issues? For the first issue, we introduce a new idea, which is called the uniform adaptive sampling. So let me recall the linear time approach. Basically, we select the big Q, and we randomly select one point, small q, from big Q. And as I just mentioned, with the probability delta over 1 plus delta, the small q belongs to the set of optimal inlayers. So this is a linear time approach. For our sublinear time approach, we take a uniform sample of n prime points from the input first. So you can see that the value of n prime is independent of n and d. Okay, and then this part is the uniform sampling part, and then we select q prime, which is the furthest 3 over 2 times 1 plus delta times gamma n prime points from the sample. So this is the adaptive sampling approach, adaptive sampling step. So for q prime, we randomly pick one point, say small q, and then we can prove with the probability delta over 3 times 1 plus delta, the small q, belongs to the set of optimal inlayers. So you can see this is a two-level sampling procedure, uniform and adaptive sampling. So by using this approach, we can avoid the linear time complexity. And then we consider the second issue. Suppose we are given a candidate solution OI, we need to estimate its objective value in sublinear time. So here is a straightforward idea. We just need to find the 1 plus delta times gamma n plus 1's furthest point to OI, and we return this distance from Q and OI. But obviously, this approach will take linear time, right? So how to reduce the complexity to be sublinear. So here we introduce the sandwich lemma. We still take a uniform sample first, having the sample have the size n prime prime. You can see the value of n prime prime is also independent of n and d. And then we take the point q tilde, which is 1 plus delta square times gamma n prime prime plus 1's furthest points from the sample to OI, and we focus on this distance, Li tilde, which is the distance between Q tilde and OI, and to estimate the range of this value, we have two carefully designed values, Li and Li prime tilde. So we prove that Li tilde is bounded by these two values. Then we can use this value as estimation. So intuitively, if you look at this figure, we can see Li tilde is sandwiched by this lower and upper bound. So we can prove that we can safely use this value as an estimation for the objective value of OI. Okay, so if we put everything together, we can achieve the sublinear time back criteria approximation algorithm for MEB with outliers. So actually the sample size is independent of the input size ND. Basically, it's independent of the number of input point N and also the dimensionality D. Okay, so finally we consider to generalize the idea. For MEB problem, when we define a ball in the space, we have 3K components. The center, right, which is the ball center, and the size, which is the ball radius. And also we have the distance function, which is the distance from a point to the center. Basically, for any point, we can define the distance function from this point to this ball, which is the Euclidean distance from the point to the ball center. So we can also define other shape very naturally by these three components, like K-center clustering. The center should be the site of K-ball centers, and the size should be the maxima radius, because for K-center clustering, we want to minimize the maxima radius. So that's why we use the maxima radius as a size. And also, the distance function should be the distance from a point to its nearest ball center. And for flight fitting, the center should be the central flight, and the size should be the maximum orthogonal distance from the input points to the central flight, because we want to minimize the maximum orthogonal distance. And the distance function is the orthogonal distance from a point to the central flight. And for one class SVM, it's a little bit complicated. The center is the normal vector of the decision hyperplane, right? Because once the normal vector is fixed, the hyperplane is also fixed. And the size is the inverse distance from the origin to the separating hyperplane. So here, because, as I just mentioned, SVM is the maximization problem. We want to maximize the distance from the origin to the separating hyperplane. So if we want to transfer the problem to a minimization problem, we just use the inverse distance as the objective function. And also we define the distance function to be the negative inner product of a point and the normal vector. So here we use a very special distance function because it's just a convenient for our following analysis for SVM. And also all of these MEX problems can be solved by some greedy algorithm like MEB. We can use the BC's coset construction, right? It's a very standard greedy algorithm. And for K-center clustering, if we assume K is constant, we can also use a coset construction idea to solve the K-center clustering problem. And for flight fitting and the one-class SVM, there are also the corresponding greedy algorithms And for two-class SVM, actually we can transform it to be a one-class SVM problem by computing the polytope distance of the Minkowski difference of the two classes. So by using the defined center, size, and the distance function, we can generalize our proposed uniform adaptive sampling method and sandwich lemma to solve this MEX with Outliers problems, and we achieve their sublinear time algorithms respectively. So one thing we should emphasize is that for each algorithm, the sample size is independent of the dimensionality. So this is a key difference with the VC dimension-based sampling approach.